Hello and welcome to Lab 5. I'm Emma Heller. The purpose of this lab was to examine the interaction between the magnetic fields of a falling magnet and the induced current in a tube of aluminum foil by collecting data on the magnet falling through the tube and then actually modeling the interaction between the bar magnet and the aluminum tube on glow script so I could later compare the data. In this lab, we use Faraday's law, which states that any change in the magnetic flux will cause a voltage or EMF to be induced. We will use this law in the lab to calculate the current in each ring of the tube. Biot-Savart's law also plays an important role in this lab because we'll use it to calculate the force on each current-carrying ring of the tube. Lenz's law is also used because we will use this to examine the direction of the induced current. Finally, both Newton's third and second laws are also applicable. I found in this lab, the experimental portion of it, I found 1.222 seconds was the time for the magnet to fall through the tube, whereas when I did it with my code, I found it to be 1.018 seconds. In this lab, we first found the north pole of the magnet and then dropped it through the tube, took a video of the magnet, and then recorded the time and repeated it 4 more times and took the average of the 5 experiments. We had to use an aluminum tube in the experiments and not a ferrous tube so that the magnet would not be attracted and stick to the tube such as it would if the tube was made out of steel. Here's my data for the 5 trials. Like I said before, I found the average time to be 1.222 seconds. In the experiment, I observed that the magnet was moving slower in the tube than if it had fallen in free space outside of the tube, and this is because the magnetic fields from the induced current opposes a change in flux, which is just Lenz's law, and that's what's causing the magnet to slow down. So here's my code. First, I set up my constants, and then I created a velocity versus time graph, and finally I created the tube of aluminum foil, which was just a stack of non-interacting conductive rings. And then when I created the bar magnet, I set my magnetic moment of the bar magnet here, and I just calculated that using my magnometer app. Then I calculated the magnetic field at a position relative to a bar magnet, and we can describe the bar magnetic field using this expression here. And then knowing the magnetic field, we can then calculate the magnetic flux, and as the magnet falls, the flux changes in time, so you actually must take the time derivative using this expression, and that's exactly what we did in the code. So you can see that in step 6. We then created a loop to simulate the magnet being dropped through the tube and calculated both the magnetic and gravitational forces acting on the magnet. And according to Faraday's law, the derivative of the flux in respect to time is equal to the EMF. So we used Faraday's law to actually solve for current, and that's what we did in step 9. And then we set the color of each ring according to the direction of current. Finally, we computed the magnetic field at each ring and used the Biot-Savart's law to calculate the force exerted on each current-carrying ring. We used Newton's third law because the force of the magnet on the ring must be equal and opposite to the force exerted on the falling magnet by the whole tube of current-carrying rings. And after calculating the net force and using Newton's second law, we actually wrote a position and velocity updating code to model the motion of the falling magnet. So here's my model. And it's showing the position and movement of the magnet through the tube, and the graph below shows the velocity as the magnet moves through the tube. Now let's interpret this model. So the direction of currents can be explained by Lenz's law, and since the magnet is falling downward, the change in flux increases in the negative y direction. So we can see this induces a current in the counterclockwise direction below the magnet, so it can oppose the flux. And that counterclockwise current is exhibited here as the blue ring. Whereas above the magnet, there's a clockwise current, which is red. So the section of the code below just shows how the ring color was set. And if the magnet was turned, so the south pole enters the tube first, it would take the same amount of time for the magnet to fall through the tube, but the induced current flips. So above the magnet, it has a counterclockwise current, and below the magnet, there's a clockwise current. Comparing my experimental data to my code data, my experimental time was more than the time I got from my code, and this could have just been due to human error. And in order to make my computational experiment more accurate, the tube could have been divided into more rings. The velocity versus time plot tells us the magnet travels at a constant velocity through the tube, which means that it's not accelerating. And according to Newton's second law, the net force must be 0 there. So gravitational and magnetic force are equal and opposite when the magnet is in the tube. For my what if questions, if the resistivity of the conductor was reduced to close to 0, then the current would increase, in turn increasing the magnetic force, which opposes the gravitational force. So the magnet would move through the tube at a slower rate, possibly stopping inside the tube. If slots were cut into the tube, the magnet would most likely speed up. And this is because there'd be less rings, so there would be a lower induced current, decreasing the magnetic force, which opposes gravitational force, so the magnet would speed up. In conclusion, when the magnet falls through the tube, it induces a current through the tube which makes the magnet fall slower. To have an induced current, the tube must be made out of a conductor. And this lab also explored several physics principles mentioned below. Thanks for watching.